Nice, beautiful rainy day.
This meeting is being recorded.
Thanks for
Sorry.
letting me know it's recorded.
Yeah.
And welcome everybody. Today I want to talk about a couple um, fun things on the intersection between sort of privacy attack performance and machine unlearning. Um, sort of to start off, we all sort of know that models are being trained on private data these days, being trained on things like emails, medical images, text messages, and the sort. And we also kind of know that there are ways that models aren't particularly good at protecting privacy. So they can be vulnerable to things like membership inference, where the goal of the adversary is to determine whether some target record was contained in the training set of a model or not. There's also sort of more scary attacks where you can sort of pull training data out of models, and this is a scary threat that's being shown for lots of these large language models these days. And there's also this like interesting line of work showing that you might need to do this, you might need to be vulnerable to these kinds of attacks in order to have accurate models. So it's a little bit worrisome of a situation. And one way that sort of regulation and folks have decided to sort of counteract this risk, this privacy risk of training on data is allowing users to delete their data from a data set that was used to train a model. So you train a model on some big database, and then a user comes along. This is a little picture of Bob here, and he says, "I want you to delete my data." And then you have to go back and you have to retrain your model without that data point. And this has been considered in ways that sort of you can do this where it's more efficient to delete this data and stuff like this because retraining is slow. But this is a sort of primitive that has been considered for helping people have more control over their data. And what I want to talk about is two sort of ways that this interacts with privacy attacks. The first is, how does this machine unlearning primitive impact membership inference? You might already be thinking about some papers that exist from people in this talk, but I'm going to be talking about a little bit of a different angle from those. And if you don't know what I'm talking about, I'll describe that. And then I also want to talk about how in some sense, if you think about membership inference as the goal of machine unlearning, making membership inference impossible, it sort of somewhat happens naturally over the course of training, with some caveats that I'll talk about when I get to that part. Awesome. So before I continue much further, I want to sort of make sure we're on the same page about membership inference. This is again, the goal is to determine whether some target record was used in the training of this model. This was originally considered for like genetic data analysis kinds of tasks. Maybe you don't want your whether you were contained in some genetic data release about cancer patients. You don't want that released to the world. And it was extended to machine learning in 2017 and has become a very popular area since. And sort of the way that these like early attacks kind of work is essentially they exploit overfitting on the models. So like one way that you can be vulnerable to membership inference is if you train a model that has 100% training accuracy and 50% test accuracy. And now if I give you 1,000 points and 500 of them are in training and 500 in test, what you can do is you can guess, is this point correctly classified by the model? I'm going to guess that it's in the training set. If it's incorrectly classified, I'll guess it's in the test set. And this test actually gives you 75% membership inference. And there's been a lot of other ways that people have improved this, looking at things like the loss, the distance to decision boundary, loss under noise, entropy. There's a whole host of ways that people have looked at this. And right now, what it seems like the state of the art is this attack called Lyra. And essentially the way that this happens, the way that you run this attack, is you train a ton of shadow models. So the way that you do this is you sort of make sure that every single model, every point that you want to do membership inference on has a 50% probability of being contained in that model. And so what you can do is you train, let's say, 100 models, and then you end up with, over your whole data set, every point is in around 50 of those models. And from this, you can sort of get a sense of what the model's confidence or logits or some score is like when it's contained in the training set and when it's not. And then you'll be able to fit distributions to these and perform a likelihood ratio test to run the attack. And one sort of outcome of this work is that it's pretty unclear exactly, so essentially, there's a lot of different points that have different success rates according to this attack. Some points are a lot more vulnerable, a lot more sensitive to this kind of attack than others. And these, I kind of think of these as like outliers. Outliers are more vulnerable. And what I mean by an outlier, I think everyone has their own definition. Here, it's essentially you need to have the point included in the training set to get good accuracy or good loss on this point. And when you're talking about membership inference, this is a bit of a circular definition. If I'm telling you that you need to have the point in the training set to get good accuracy on it, essentially that's saying the distributions of the in and out sort of losses or whatever score are going to be very similar to each other. And we haven't really gotten anywhere. But at least you can think like there are easy to fit points and hard to fit points. Hard to fit points tend to seem more vulnerable to these attacks. And all right, so now I want to jump into machine unlearning, and sort of I want to start with maybe the first question about machine unlearning and membership inference that you would ask, which is if I do machine unlearning on a point, how does that impact the vulnerability to membership inference on that point? And folks here have actually looked at this. Essentially what you get is if you are able to look at both models, if your adversary can see both the model that had the point in it and the point out of it, where the point was in the data set and where the point was out of the data set, then you can actually compare the two and then do membership inference much better than if you had only seen one of these models. So that's sort of the first result on membership inference and machine unlearning. And then you can also ask sort of what happens to other points. That's what I'm going to talk about next. And to start, I want you to sort of just look at this graph. So what this graph has is for every example in CFAR 10, it has the attack success rate of that Lyra attack. So over 100 models, over on the right, it succeeds something like 99 times, and then sort of on the left, it succeeds only with 50% probability. And so one thing you might think to do is you want your model to sort of be more private. And one thing you might try is, okay, I'm going to remove every point that has more than some membership inference accuracy. And your hope is that by removing these points, maybe in machine learning, maybe you're sort of doing this before you release any model at all. Your hope is that now every point is going to have less than like this 82% membership inference, and you've made the model more private. And this is a reasonable thing to think. Essentially, all you're relying on here is that all of these membership inference accuracies are independent of each other. But it turns out that what actually happens when you remove these points is you end up with this not being the case. There's still a significant amount of points that are above 82% accuracy. And sort of, if they were all independent, you would see nothing to the right of this line, but it just turns out that you do. And we call this the privacy onion effect, because you're sort of peeling off the first layer of vulnerable points, and you find that there's another layer that looks just like it, waiting for you when you peel this off. And so what we wanted to figure out is why this happens. And to start, I think I was very confused when I saw this effect, for the first time. And I'm hoping that you all are too, because it's unclear that why this should happen, and everything. So I want to just sort of start you out with something a little bit simple, a case where this can happen in a very, very simple fashion, to sort of tell you, this might not be so weird. So we're going to be looking at this two-class binary classification problem. We're distinguishing circles from squares. And what we're going to do is we're going to train a linear SVM on this data set, and it's going to produce this. And SVM, support vector machine, has the property that you can sort of describe it completely by its support vectors. So I can give you this data set, tell you to train an SVM, and I can also give you this data set and tell you to train an SVM, and you'll end up with the same model. And so what you can think about is you're not leaking anything about these other points. The model doesn't depend on them at all, but you're sort of leaking everything about the support vectors. You need them sort of to describe the model. And so, you can, let's say, do 100% membership inference accuracy on the support vectors, 50% on the others. And so if you did the privacy onion effect, if you tried to remove that first layer of onions, which are the support vectors, of course, a support vector machine needs support vectors. And so you'll end up with some new support vectors. And these will be the new points that are leaked. So you always need to have some points that are leaked by this SVM. And so this is one setting where the sort of privacy onion effect does show up. But things don't necessarily transfer from two-class linear SVMs to things like neural networks. So we did a little bit more investigation on that CFAR example. So I'm going to sort of walk you through a couple potential hypotheses that could describe why the privacy onion effect happens. And then I'm going to sort of tell you how we decided whether that is the correct thing or the incorrect explanation. And the first is very simple. We threw out every point that had 82% membership inference accuracy or higher. It could just be that these are very noisy quantities. I measured a point with 81% membership inference accuracy, but it turns out that this could have been anywhere from 75 to 90. And I just got unlucky when I threw out these points that were greater than 82%. And it turns out this isn't the case. And the way that one way you can do this is you can train 200,000 models. And it turns out that when you get to this point, like the effect still happens. And so we can be pretty confident that this isn't just experimental noise. As a bit of an aside, I do kind of like there's been a couple papers that I've written that have trained a lot of models. So there's this paper called Auditing DPSGD, so Differentially Private Stochastic Gradient Descent. We trained 1 million fashion MNIST models for this. So this is even more than this data set, or than this paper. But this was CFAR models, and it's a lot easier to train fashion MNIST. But I think the record, as far as I'm aware, was broken by, there was this paper on doing DPSGD better that I think was presented here. And to do the auditing technique for this, I think they trained a couple million models. So, it's not too bad to have the record beaten by DeepMind when it comes to compute. Okay, so it's not a noisy sort of attack success rate measurement. One other thing you might think is it's a small data set, a smaller data set. So if I tell you that you train a model on 50,000 points and you run an attack versus a model trained on 45,000 points, the same model, you might expect that just because there's 5,000 fewer points, there's more information encoded per point. And so all these membership inference accuracies are going to go up. And so sort of on the left, I'm showing you the original experiment. We have 45,000 CFAR10 inliers, 5,000 CFAR10 outliers. In one experiment that you can run to test if this smaller data set hypothesis is the correct explanation, is instead you can remove 5,000 inliers and leave the 45,000 outliers. And if the smaller data set was the thing that caused this onion effect, then removing these inliers would also increase membership inference accuracy on the outliers. But it turns out that it doesn't. And so we can sort of rule out this hypothesis. Smaller data sets, not the effect. A somewhat related one that's also kind of related to the SVM example is that we just have a limited model capacity. So the model is only capable of memorizing 5,000 points and sort of being vulnerable to membership inference on these 5,000 points. And so what you would expect if this is the case is essentially you remove the 5,000 points, and then the model's sort of freed up some of its memorization ability. And so now there's a new 5,000 points that can sort of fill in those that spot that can be memorized again. And so again, here's our original experiment. And then the one that we use to test this is we take the same 45,000 CFAR10 inliers, and then we add completely arbitrary outliers, things that the model would need to memorize in order to sort of get good loss on them. The specific thing we did here was we took like CFAR 100 examples with completely random labels. And you would expect, if the model only has a limited amount of capacity to sort of memorize these points and be vulnerable to membership inference, you would expect that adding these arbitrary outliers would sort of have the same effect on the CFAR 10 inliers. You would have an onion effect where removing these outliers gives you better membership inference, adding them gives you worse membership inference on the inliers. And it turns out that this also isn't the case. The model is perfectly happy to memorize the CFAR 10 inliers and the arbitrary outliers both. And so there's sort of more memorization going on the right. And so it's not a limited model capacity effect. Another thing that you might think is duplication. And I want to talk about this one a little bit more because it's kind of close to what the truth is. And so, okay, I'm going to give you this little picture. And what this is we have 2 points that are near duplicates of each other in our training set. And in the membership inference experiment, every point has, let's say, 50% probability of being included. And so we end up with 4 equally likely outcomes with regards to these 2 points. We have a situation where both of them are in the training set, a situation where both of them are out of the training set, both that happen a quarter of the time. And then we also have these 2 equally likely outcomes where one of them is in the training set. And if you train the model on 2 things that are near duplicates of each other, only one of them, like the models are going to be very similar. They're going to be very hard to tell apart. And so because these are so similar, you won't be able to do membership inference better than 50% at distinguishing between the case where only one of them is in, and you want to guess which one. And then you can do perfect membership inference, say on the outside, but you're still capped at around 75% membership inference because of the duplication. And so in some sense, having this duplication here masks the ability to do membership inference on any individual point. And it turns out that if you do remove the duplicates, a lot of these points do have their membership inference success rates go up. They become more vulnerable. But this doesn't explain the whole effect, why all of these points sort of are vulnerable or are impacted by this privacy onion effect. And the explanation that we ended up with is that sort of it's a little bit more general than this duplication story. And essentially, there are sort of outliers that are masking other examples in the training set. And sort of as an example of this, we have this deer here on the left. This is obvious to the model that it's a deer. If you're not as familiar with 32 by 32 images, it's maybe a little harder for you to tell. But you know, it's a deer. It's very clear deer to the model, and it has an original attack success rate of 66% when you do the standard all 50,000 point experiment. And it turns out that its attack success rate goes up when you do the privacy onion, but it also turns out that there's only 10 examples that you can remove, the ones that I'm showing you on the right, that can sort of cause the onion effect already. You can get this point from 66 to 81% membership inference accuracy for this point. And so essentially, all this is saying is you just need these other sort of more strong outliers to be removed to cause the onion effect. And it's more of a sort of local effect than it is a global effect. Yeah, so also I can't see if anyone's asking questions. If any of them do show up, I'm happy to answer them. I'm just on the screen for the slides. And I would expect some questions by the time that I'm here.
Right, Matthew. So I got
if anyone wants to sort of stop me and ask anything, this is a good point to do that.
Matthew, can you hear me?
Yeah.
Okay. So I got one question here. So for example here, after removing these examples, you mean this accuracy for this deer's membership inference goes up, but the samples the examples you removed, are they outliers, or?
I think that these are points that have higher membership inference than this sort of deer on the left beforehand. I didn't actually look. All I know is that if you do remove these 10 points, it does have a huge impact on this point on the left.
So probably I missed something, but how do you choose these 10 points? Like
yes, this is tricky. So essentially what you can do is if you train enough models, then you can get a good sense for sort of pairwise correlations in this membership inference accuracy. So basically, you've seen enough models that are trained without this sort of first point, which is this like deer that's sitting in a pasture. It's a smaller deer. The 10 examples, the one on the left. You've seen enough models such that you can estimate the membership inference accuracy on the sort of target point when this point is not included. And so you sort of just sort all of the examples based on that membership inference accuracy. So you do sort of a greedy algorithm to select these 10 points once you have the membership inference accuracies.
And when you mentioned it, yes, okay, I got it. But this you need to train a lot of models actually. But yes.
Yes. Yeah.
So the thing is, like you mentioned, your explanation here is this outliers masking other examples. So this is true for all. I mean, since you have many samples and you have many experiment settings to do, so I suppose you also have many such kind of images. So almost all of them because of this masking effect.
So yeah, this is actually and not only do you need to train a lot of models, it's also pretty computationally expensive to sort of compare all these, like, you know, like this ends up being like a couple like 50,000 by 50,000 matrices. So we only looked at like a couple different types of points. And it does turn out, so the kinds that we looked at, one is the duplicates. So can you sort of use this same sort of effect where you greedily pick points to increase membership inference accuracy? Can you do the same thing to identify the duplicates that had a big effect on increasing membership inference accuracy? It turns out that you can do this. So this is another way to sort of validate this. And then we also looked at, like, there's some points that you get like 51% membership inference accuracy on if you're not removing any points at all. And it turns out that you can even increase these points by several percentage points by removing points. What actually we didn't do was go back and like sample from these like sort of top or the sort of no, sorry. This deer is it's one of the examples that increased the most as a result of removing the 5,000, and it gets up like we looked at a couple examples like this, and this is pretty, like, you do get like most, at least, of the onion effect from this sort of like smaller set of examples that you remove, which of course is dependent on the point.
Great. Okay,
sorry, thanks. Answer the question?
Yes, okay. Yes, thanks. Yeah.
Mm-hmm. If anyone else has questions, feel free to ask. If not, I have sort of a little bit of a takeaway slide. So one is one takeaway that I think is kind of cute of this is sort of you could identify these sort of 10 examples, and if you were an adversary, you could use these 10 examples and sort of if you were an adversary that had the ability to sort of arbitrarily choose which points are machine unlearned, you could do this and you could increase membership inference accuracy on other points. I don't know if there's any like reasonable adversary where you can do this, where you have the power to sort of issue arbitrary machine unlearning requests, but not sort of know what points are members anyways. But if there's a threat model where you can do this, I think it's kind of cute that you can sort of just use this machine unlearning primitive to increase membership inference for other points. Another impact that's maybe a little bit more clear is in like a benign setting. These unlearning decisions do impact other users. So my decision to unlearn might impact the privacy of someone else. And one thing this means is that these privacy tests that people run on these models are very sensitive to these very small changes in the data set. 1 point's membership inference can increase by 15% accuracy when you sort of take out only 10 points. And sort of on this, I wanted to briefly talk about another example where this small changes in the data set can have a big impact on membership inference accuracy. But instead of by removing points, it's about adding points. Cool. If there are no more questions, then I'll hop over to that. So essentially, the idea here is we have an adversary who not only is trying to determine this target record, whether it's in the training set or not, but they're also able to add examples into the training set. So they're able to add some poisoning. Here you can imagine that they're doing this in a multi-party computation. You're sort of training a model between 10 people. I want to be able to do membership inference on some other person in this MPC process, and I'm going to add poison data into my local data set in order to do this. And it turns out the sort of message of this work is that you can do attribute inference and training data extraction and membership inference all a lot better as a result of this poisoning attack. And there have been similar results that folks have shown for property inference attacks, which is looking at sort of more global properties of the data set. Can you determine how many women were used to train a model, the gender distribution or something like this? You can infer this also better with poisoning. And to give you a little bit of intuition for this one, I want to show you the exact same binary classification data set. And our goal is to determine whether this one little square was contained in the training set or not. So it turns out that if this point was in the model or not, the sort of 3 nearest neighbors decision boundary ends up being exactly the same, at least if I drew this correctly. There's a lot of points where this happens, like if they're sort of far from all the blue points, you would expect that including any one of these green squares isn't going to do much. But it turns out that you can do poisoning to actually reveal whether this one point was in the training set. And I'm going to show you how. We're going to add 3 points into the training set. And one of them is going to be from the same class. It's also going to be a square, and it's going to be very, very close to this example. The other one's going to be from the opposite class, and it's also going to be very close to the example. And then one is going to be also from the opposite class, but we're going to put it a little farther away, but not so far that there's any other training example near this point. And so what we're going to do, or what we see is that if this example is in the training set, then when you run, when you sort of query, what is the label for the example, then what you're going to see are the 3 nearest neighbors are those 2 very close points, one which was opposite, one which was same class, and then sort of the tie will be broken by that example. And so you'll see that it correctly classifies this point if it is in the training set. But if it's out of the training set, then the tie is going to be broken by this nearby opposite class point. And so you're going to get that the classification is incorrect on this example. And so this perfectly distinguishes between the in and out settings, and you can do perfect membership inference in here. And it turns out that attacking neural networks, it's a much simpler task. You don't need to do any fancy breaking ties or anything. It turns out that sort of all you need to do is flip the label. So you take this picture of the frog, you add it with some incorrect labels, and you can see here with no poisoning, the 2 distributions, the sort of non-member distribution in blue and the member distribution in red, are basically indistinguishable. But when you add 1 poison point with the incorrect label, if the point is contained in the training set, they're sort of going to fight against each other, the poisoning and the correct label. But if it's not contained in the training set, the poisoning will have more sort of power. It won't be opposed by the correct class. And it turns out that if you add more points, these distributions get further apart. And if you add up to 16 points, this one frog, which had essentially 50% membership inference accuracy before, now the distributions are almost perfectly distinguishable. And this essentially shows that just by adding a small number of points, you can control membership inference accuracy on other examples. And so this is another sort of example where these privacy tests that you might want to run are very sensitive to small changes in your data set. Another thing is if sort of you did machine unlearning on the poison points, this would be a case where membership inference would get better on an example if you remove examples. So the sort of onion effect doesn't necessarily have to increase membership inference, but you would need to have some sort of outliers which are opposite class that will sort of make things worse for that example. Okay. Are there any questions on this? I know actually that Florian Tramer, who I worked with on this this sort of poisoning attack, I know he gave a talk here, so this might have been review. But if there are any questions, I'm happy to take them on this poisoning stuff. Otherwise, I'll continue on. Yeah, Ziqing.
Hello, thanks for your presentation. I have a question regarding the poisoning attack in your last slides.
Yeah.
Page 39. Yeah. I wonder here for the poisoning samples, how you choose the poisoning samples and what the goal for your poisoning.
Yeah, so if you're thinking about this as a poisoning attack, you can even think about this as a targeted attack on this frog. So you want to change this frog to some arbitrary incorrect label. And it turns out that, and sort of the way that this is not like a clean label attack. It's not using any sophisticated sort of poisoning techniques from that literature. All it's doing is adding this exact frog with an incorrect label. That's consistent between all 16 examples.
So here for the poisoning labels, for more poisoning samples, the flipped label is the same. They are not flipping to other multiple labels, right?
Yeah, that's important.
Okay, get it. Thanks.
Yeah, no, thanks for the question.
Hi, Matthew. Can you hear me?
Yep. No.
I just directly asked, sorry, Elon. And so here you poisoned 16 exactly same images, and I'm wondering, does it because the duplication of this exact image and the exact flipped labels that increase this difference?
Yeah, so it's not clear to me that this is something that would always happen. Like you might imagine that when you have 16 mislabeled examples, it might just, in some models, it might not matter at all whether there is one correctly classified example. But it just turns out for sort of cross entropy loss that that sort of 16 versus 0 is a much different fight than 16 versus 1. And yeah, like because the 16 points are all working together, you do end up like shifting this this loss a lot. Is that sort of what you're asking?
Yes. So actually, I'm wondering why this could happen, because if this is a real world attack, it could be easily detected, and if this just a testing to see how many images I need to poison to distinguish or to achieve my goal, I think maybe there's some duplication effect here to make the poison attack success.
Yeah, so if you're thinking about this as whether someone would actually run this, you can think about like in an MPC setting, it's a little bit tough to sort of force someone to deduplicate their data with reference to your data. You know, this might be itself a privacy leakage. Mm-hmm. So you could imagine this kind of thing happening very well in an MPC setting. In other settings, it probably just comes down to the threat model, whether this is reasonable. One thing that you can do is you can actually add poisoning that's not an exact duplicate, and it will work a little bit worse, but still well. You'll still get a better effect than if you didn't add poisoning at all. And you can even query not on the exact point. You can query on that nearby point, as long as it's sort of still flip labeled, and you'll still observe this effect.
Okay, thanks. So another question, does the label that choose to flip or the target label matters?
Yeah, so we tried a couple things on the attacker label. It turns out that like the best thing you can do here is just randomly picking an incorrect label. Like you could imagine that sort of picking the label that is lowest predicted or even second, like highest predicted by the model, like this would do better. And it turns out that it doesn't. Like just randomly picking a label and going with it ends up giving you the best attack. At least the best attack applied to sort of all points at once. Like there's probably some best label for each point to attack with, but it's not consistently the lowest predicted label or the second highest predicted label. Random seems to do a lot better there.
Yeah, I understand. Thank you.
Cool. Yeah.
What do the horizontal and vertical axes represent in these figures?
Yeah, so this is just a histogram of some, you can think of these as loss values. So the further left you are, the sort of worse you're doing on the example. And like sort of your low loss is to the right, high loss is to the left. And so when you add poisoning, it goes to the left, the loss increases because you're adding incorrect labels. And yeah, that's the effect that you see here. And you also see that it gets more distinguishable.
So the red part corresponds to the loss after poisoning.
The red part and the blue part are both with poisoning. The red part is where the example is contained in the training set. So it's sort of the in distribution.
Oh.
And the blue part is the out distribution, where it's not in the training set.
Oh,
and so
see.
membership inference works if these distributions are very different, and poisoning makes them very different.
Okay, thank you.
Mm-hmm. Cool. If there are no more questions, then I'll continue. Okay, so yeah, now I'm shifting. I'm going to talk now about sort of how membership inference decreases over the course of training, and this is an effect we call forgetting. And the setting that I want to describe is one where you sort of make one pass over a training set. So we start by updating some model on X1, and then we take that model and we update it on X2, and then X3, and so on, up until Xn, and n is a very large number. We're updating with a ton of points, and every single point, once it's updated once, you never see it again. And this is actually a very common setting these days for like large language models. These data sets are hundreds of gigabytes, and so you can't possibly like go through all of them multiple times. You can't make multiple epochs. And so the sort of question that we want to ask is, does X1 have better privacy than Xn? Intuitively, it should be the case, right? Like you haven't seen this in so long, and hundreds of gigabytes of data, that it should be very difficult to tell whether this point is still in the training set. But it's also not clear. Like X1 might sort of determine the entire trajectory of optimization, and that's possible. And it turns out that if your training algorithm is differentially private and you add some other assumptions on the model, then this is provably the case. X1 is provably more private, has a lower sort of differential privacy epsilon than Xn. This is a result known as amplification by iteration, and it's a very cool result. But the thing is, not all models are being trained with differential privacy, and not all of them satisfy these assumptions, which include convexity. And lots of deep learning is, or basically all deep learning is non-convex. So for standard training algorithms, the best we can do for now is just to measure whether this sort of vulnerability changes over the course of training. And the way we're going to do this is we're going to sort of start out this training process like normal. We update on X1, X2, X3, and then we're going to sort of branch the training. So we're going to have some points that we inject into the training set, and then we're going to continue training. So here I'm saying X4 through Xn. We might also sort of shuffle and sort of hope that shuffling will sort of give us something, or where there's some non-determinism in the training, because if it's exactly deterministic, we'll show that actually you can always do membership inference. And sort of so over the course of training, what we're going to do is we're just going to test. Can we distinguish between these two models? And if we can distinguish between these two models, then sort of the sort of XA is still having some influence on the model. you can still do membership inference, and you don't get this sort of forgetting effect. And so what we're going to do is just sort of over the course of training, from step X4 to step Xn, we're just going to see what membership inference looks like. And it turns out that you get this like nice steady decrease in membership inference accuracy over the course of training, but it does take a long time. So here what I'm showing you is the precision of membership inference at some fixed false positive rate as a course of as a function of how long after this point was added into the training set. And I'm breaking this down into 3 different groups. One is sort of hard examples, which are actually big outliers. And then in the orange, we have a medium hardness examples, and then we have very easy examples in the green. And so this is showing that this membership inference attack is working quite well on the hard examples, which sort of corroborates the sort of outliers are more vulnerable story that we talked about earlier. And it's essentially forgotten almost instantly for these easy examples where membership inference is hard to do. And so like this is just sort of saying like this sort of effect does actually happen. And you know, the extent to which it happens is sort of what you need in order to make a decision about this. For example, if you're not okay with 60% membership inference accuracy, then or precision, then you know 14,000 epochs, 14,000 steps after the injection. The hard examples, you can still get more than 60% membership inference precision. And so this wouldn't be good enough for you if that was your cutoff. But you might expect that if you continued even further, I don't have the data for that, that this would go down even more. And sort of to explain, we sort of just saw that this thing happens, and we also wanted to explain it, like to see what's going on with this effect. And to do this, we first looked at a couple different situations where it doesn't happen, where you can show that it doesn't, you don't get this forgetting effect. One of these is if you sort of have no non-determinism. So on FashionMnist, what we did is we started training a model with a fixed batch order. So essentially, every single step is exactly the same, except for this one injected example, or we have some injected batch. And so every single step are going to be the same up until you sort of branch the models. And then you add this injected point, it'll shift the model by some amount, and then you continue making steps on the exact same examples. And turns out that this allows you to do almost perfect membership inference for 95 more epochs. And sort of this membership inference accuracy is just still very high. And this is just because you're making the exact same steps. And so this one shift is always going to persist in the model. And we actually have some sort of theoretical discussion showing that if you don't have a known batch order, if the adversary doesn't know exactly all of the examples and sort of exactly the batch order, this can cause forgetting in a very simple case in sort of a SGD on mean estimation setting. Another case where forgetting doesn't happen is when your models are non-convex. And so this sort of corroborates the convexity requirement from the differential privacy amplification by iteration work. And sort of to set this up, what we're going to do is we're going to look at k-means, which is probably the simplest non-convex model class that you can sort of wrap your head around. And to show that it prevents forgetting, what we're going to do is we're going to set up a non-convex k-means problem where we have 3 clusters in the data. We have this blue cluster on the left, green cluster in the middle, and orange cluster on the right. And we're going to set k equals to 2. K-means needs to find 2 clusters that describe these 3 well. And so because this green cluster is in the middle, the choice is essentially going to be, do we merge the green cluster with the blue one or the green cluster with the orange one? And it turns out that in the data set that we're going to use, or sort of the data set we're going to set up, the green cluster is naturally closer to the orange cluster. And so if you sort of ran k-means normally, it would merge those 2. It would merge orange and green, and blue would be on its own. But we're going to start with this initial training set that has this outlier where the green point is closer to the blue cluster. And so what you'll end up getting is that here, it'll merge the sort of left two, the blue and the green, instead of the orange. So the outlier is sort of changing which merging happens. And so it turns out that this is the case. If you sort of do this experiment, you'll see that the blue and the green get sort of merged together when it's in, and nothing will happen if it's out, but the orange will still be closer to the green. And so then what you do is sort of to see if forgetting happens, you remove all of this original data set, and then you add new data samples from each of the 3 clusters. And what you can see is that if you start with the initialization that was learned from the original data set, then the outlier doesn't get forgotten. So sort of the decision made by this outlier, whether it was in or not, will persist through the course of training, even if you sample new data randomly from this distribution. Just the non-convexity, the fact that you end up in one of the 2 local optima because of this one outlier example, that will persist over the course of training. And so non-convexity here can prevent forgetting. What's interesting is sort of in our results, we looked at model classes that are all non-convex. These are all sort of state-of-the-art neural networks, all very non-convex models, and we don't see that this kind of forgetting effect happens. And so this sort of begs the question, like, one of these things is wrong, right? Like either non-convexity doesn't matter for this kind of forgetting effect, which I don't feel like I can wrap my head quite around, or we might need some non-convexity aware membership inference attacks. So what I mean by this is I'm not aware of any membership inference attacks that sort of exploit the optimization trajectory. And this might be needed if you're going to be able to do membership inference on that first example in your long training run. You might not be able to rely on sort of standard attacks. One other takeaway from this is for its sort of application to machine unlearning. So if you think of machine unlearning as you get 50% membership inference accuracy, then sort of over time, just standard training might satisfy that. And this sort of leads to questions about what you actually mean when you mean unlearning, and this probably isn't just the right way to think about it, and you might need this sort of active thing to guarantee a stronger property that you might want from machine unlearning. And finally, I think there's this interesting thing here where sort of non-determinism can cause forgetting. So random batch orders and random sampling from data sets can cause this forgetting effect. And these are something that you can't rely on in sort of differential privacy analysis. And it might be interesting to see if there are any things here that are reasonable assumptions that you can make that can improve privacy analysis based on sort of some obscuring effect of the data, if that's actually possible. Cool. With that, actually, I want to say thank you for attending the talk. We looked at 3 things today. Removing and adding examples can both cause membership inference accuracy to change on other points. And as you train for a very long time, you start to forget things that happened earlier in the training process, points that were contained early in the training process. I also want to shout out my friend Isa Lee for the Alice and Bob drawings that I had during my talk. And I also want to shout out that we have a language model extraction benchmark challenge that's ongoing. If you want to dip your feet into building better training data extraction attacks for large language models, we can give you some free Colab compute in order to play around with techniques there. We have a benchmark setting for that. Great. So with that, thanks everyone, and I'm happy to take some questions.
All right. So thanks, Matthew, for the talk.